Welcome back to class number 10. Here's another example out of our book. Example 310. All right, so we have a piston cylinder setup. Looks like this below. Contains 5 kilograms of ammonia at negative 20 degrees Celsius with a quality of 25%. So now you know that it's a mix, right, with a quality. The ammonia is now heated to a positive 20 degrees Celsius, at which state the volume is observed to be 1.41 times the initial volume. Find the final pressure, the work the ammonia produced, and the heat transfer. And find my mouse. There you go. So we have ammonia. It don't smell so good. And here is the control volume that we're looking at. And what we're going to do is we're going to have some heat in, right? Because it says it's heated up, right? It's now heated, so Q in comes into there. And it's going to have some work out. So the work is going to go to the spring, right? So I didn't mean to, no dots. We don't know the flow, right? So there's the work out. And it's going to go into the spring. And because it's a spring, the pressure is going to be a linear pressure increase. That's how we know this part right there, right? So I really shouldn't show you this part of it right here because this is part of the answer that's taking place right here. But when it comes to a pressure and a volume, that's what we're that's how we know that it has a straight line, because the spring, its pressure is related to this force, and when it gets smaller and smaller and smaller, it's going to increase the amount of force in a linear manner. And of course, the pressure is just going to be that force divided by that area. So that's how we know it's a linear type of distribution. So I hope you can pick that out. So things that they told us, first off, they told us the mass was 0.4 kilograms. Good, we don't have to do anything with that. And then the temperature at the start is negative 20 degrees Celsius. And that the quality at the start was 25%. They told us that the T2 is going to be 20 degrees Celsius. That's positive. I'm not going to write the positive sign down. And then we also said that V2 was equal to 1.41 times V1. Okay. So I'm going to go to table B.2.1 in our textbook. First, I'm going to get rid of that. And ammonia, so it's B2, huh? Oh, no, wrong units. Let's see. B. You? Yeah, you. Look at you. All right, see, I was already here. Here's ammonia, saturated ammonia, and we're going to be the minus 20. And so here are the values that we need across the board. So let's write in the table there. At T equals negative 20 degrees Celsius. We might need the pressure, so let's get that 190.2 kPa. We need the VF. It's going to be 0.001504 cubic meters per kilogram. The VFG is 0.62184 cubic meters per kilogram. The UF, might as well get that, 88.76 kilojoules per kilogram. And then the UFG is going to be 1,210.7 kilojoules per kilogram. All right, so for the time being, we're good with that information. And now with this quality right here, we're able to find out what the V1 is going to be. And remember, that's just going to be VF plus X VFG. So we get 0.001504 plus 0.25 times 0.62184. And what is my value from that? Is, where'd you go? 0.15696. Boom. Okay. And U1 is going to be UF plus X times UFG. So 88.76 plus 0.25 times 1,210.7. And that turns out to be 391.43 kilojoules per kilogram. And what else do I need? Oh, all right. So they told us that this was going to be, you know, the volume after this process when it goes up to 20 degrees is going to be this amount right here. So let's find out. V2 is going to be 1.41 because it's the same mass. We could just go ahead and hit by V1. I guess I keep writing that 1.41 times 0.15696. So you get 0.22132 cubic meters per kilogram. Now we know two pieces of information. When we know about the second state, we know the 20 degrees Celsius and we know the specific volume. So we could just go ahead and look it up. So we're going to go to table B.2.2, where this is where the superheated ammonia is going to be. And so we're looking for 20 degrees Celsius, and we're looking for 0.22132. Let's get rid of this. So don't want to clean that up. All right, so we're in the superheated tables. Are we superheated? No, not yet. Now we're superheated. Okay. Is this the first part of the superheated? Sure is. Right. We started out with 800 kilopascals. That's pretty surprising. How much that is, I didn't think it would be that high. Okay. Is that true? What happened here? No, I jumped ahead. I don't know why. I looked at that. Yeah. Okay. So yeah. Okay. Here it is. So let's just start looking through these. Let's do. I think this is the first page. Is the first page of these? Yeah, I think it is. At 50 kilopascals, we're looking at 20, and we have a specific volume of 2.747. So we want 0.22. So we have a ways to go. And we could go over here and look at the 20 degrees. Oh well, we're going down. We're in the right trend. Here's 20 degrees. All right, so we got, that's, okay, we're going down, we still need to go to 0.2. Here at 20 degrees, we got 0.4, got 0.3 at 400, let's see, where did I say 20 degrees, right? 0.62, oh, wait, 0.22154. That's really close to us, all right? We needed 0.22132. Right here. So we can almost call it, man. We can always say this, it's 600 kilopascal. And I went ahead and did my interpolation to the thing, and it got really close. I got so that it was 600.7 kilopascals. So we're going to go declare this one good enough and say add P is equal to 600 kilopascals. First off, V is equal to 0.22154, and we're just ever so slightly off. So we're going to declare that good enough. Don't generally do that, but I mean, if it was an exam, I might do something like that on an exam. Just be forewarned, just to try to save you some time, so you didn't have to go crazy doing interpolations all over the place, because that's no fun. So we can also write down the U right here while we're here. And double check, yeah, that's U. So we're going to have the U is going to be 1,347.9 kilojoules per kilogram. And is there anything else I want? No, I don't think so. Boom. Oops, what happened here? There you go. All right. That scared me, man. Don't do that. Really, really, really close. All right. So what we're looking for is to find the pressure. We just found the pressure. That's going to mean we're going to say that's darn close. That's better than you can. I mean, 600.7. You read the gauges when we did the ideal gas little thing passing around in class. You can't tell 600.7. Even if it's a digital gauge, you couldn't really be assured that it was that much difference. So that's going to be close enough, I think. And then so we want to find the work. That's done, right? So the work is going to be the well, obviously it's 1 to 2 is equal to the integral of pressure per change in volume from state 1 to state 2. But we have a linear relationship, and it's easiest for us to think of this as being the area underneath here as a trapezoid. So therefore we take the average pressure and multiply it by the base, which is the change in volume. And our change in volume is on a per mass basis, so we're going to need to multiply that there. All right, so what we want to say is we have 1/2 P2 plus P1 times V2 minus V1 times M, because these are on a per mass basis. So 1/2, and just to keep the units straight, I'll be a little fussy into 190.2, no, 190,200. Remember that we got that from here. Wait, I messed up something. What did I mess up? Yeah. I guess that's actually P1. It doesn't matter. We're adding them together. Okay. That should have been the other way around. We just got 600,000. And gonna run out of room. V2. That's going to be 0.22154. Well, let me do this one up here. It's the one it should have been. Sorry. 22132. And then minus, where do we start out at? Oh, we got this right here. 15696. And then, of course, I broke, I don't know why we have the margins if we're not going to pay attention to them. Okay, whatever. They told us it was 1/2 kilogram. 1/2 kilogram. Did I say that anywhere yet? No, I guess not. Anyway, what we'll find is we have 12,725 joules, right? Because that's what Newton meters. Because I used this right here. Yeah, I'm consistent through. Wait a minute. No, I'm good because these are cubic meters per kilogram. So you could just say that I'm 12.73 kilojoules, and it's positive, so that's work into the system. This didn't matter. These would have mattered if it had given me a negative number. Then I would have been that we were. Excuse me. Let me see. No, this is work out. Yeah, I'm sorry. Yeah, this is correct because it's positive. It's work out. If it's negative, it's work in. It's a crazy convention, but it's true. And now, if we want to try to find how much heat, we go back to this U2 minus U1 is equal to Q12 minus work 1/2, right? So this sign convention is the one we need to maintain. And so what we would find is we'd have Q12 is equal to U2 minus U1 plus work 1/2. And we need to go this. We need the mass times this right here. So do I want to write it out again? I guess I do. Mass times U2 minus U1, and then plus the work 1/2. So Q 1/2 is equal to the mass which we established was 0.5, times what we found U2 was right up here. So this is U2. 1347.9 minus 391.43, boom, and then plus 12.73, and did we get it right? Sure. What we end up with is 490.96 kilojoules. That's too many sig figs. 491. I have Q. I don't have any more room. 1 to 2 is 491 kilojoules. Woo! I'm tired. Should I do the last example? I don't know. Maybe. Maybe not. Sure. I gotta check on the game. The Jets winning? No, it looks like still 20. You got 2-minute warning. Patrick Mahomes scrambles the left end for 9 yards. Oh, 1st and goal. They're just gonna knee on the Jets are out of timeouts. It's a closer game than anybody would think, huh? Surprising. Good night. No, one more. One more. Don't be lazy. Oh, I can't find my mouse.